In this last topic on chapter 13, I want to go through some properties of orbits and some topics about how to go from one orbit to the next, and a more general comment about energy. And so I want to return to the simple picture of the coordinate system in chapter 13 is that of a large, massive object that's at rest. And let's consider a satellite in uniform circular motion around it. Okay, so we're in the coordinate system of the planet, and the planet or the star is so large that it doesn't move relative to the motion of the other objects. So let's look at the map. Let's look at this. It's got a velocity v, and of course, when it's moving in a circle, it feels a force towards the center. That's the gravitational force, which corresponds to the net force. Now, again, this is what we observe on this coordinate system of the planet. When we're watching this thing orbit in the circle, we think to ourselves, well, of course it's accelerating towards the center, but the person on the object, right? The person on the object that sees the Earth rotate around it, they're in their coordinate system. You have to remember that they observe a gravitational force, but they're not accelerating relative to that coordinate system, and so they observe this inertial force that adds to zero. So both of these add to zero. So that's where we get this phenomenon of weightlessness in this system, where our gravity, as we're orbiting this planet, our gravitational force downward is balanced by a inertial force. And so there's no room for a normal force here. N would be zero if we tried to stand on a scale. And so that is the coordinate system that's rotating with the object. It's not terribly irrelevant to understanding the speed, but it's a good reminder. And so this gravitational force then, which is G big M little m over R squared, we're just going to set that equal to mv squared over R. All right, the term on the left is the magnitude of the gravitational force that the satellite feels from Newton's law of gravity. The term on the right is just the net force due to any object moving in a circle. And so a couple of things we can observe. First of all, the little m's cancel. And again, the little m's in most of these problems always cancel because we're in the coordinate system of the overwhelmingly large mass. One thing I could say up at the top here is that the mass of the planet is much, much bigger than the mass of the satellite. And so we can work in that system. And so in that case, the mass of the object doesn't really matter. But if these two objects were kind of the similar size, then sure enough, they would both be orbiting around a common center of mass. But in this case, the masses cancel. And in fact, we can cancel the R on the right with 1 on the left. Solving for V, taking the square root, we get that V sub orbit is square root G big M over R. So evidently the orbital speed of a satellite around a large massive object only depends on the size of the massive object and the particle's distance. Notice that it doesn't depend on the mass here. And that's an important topic because that means any object of any mass is going at the same speed. A way to really convince yourself of that is to think about the asteroid belt. The asteroid belt is clearly a collection of many different sizes of rocks and pebbles and boulders and mountain-sized mini asteroids and even objects that are larger still that are all orbiting at the same speed. I mean, roughly, the asteroid belt has a non-zero thickness, and so there's kind of a chain on the inside of particles that are moving slightly faster, but evidently it's not too thick to where it becomes unstable. And maybe it was thick at one time, and it became stable because it was the thickness shrunk because it was not stable, but who knows? So that is the speed of an orbit of an object. This can extend not only to communication satellites and the moon orbiting our Earth, planets orbiting our star, and there's also an interesting problem, homework problem, that you can use this to estimate the mass of the Milky Way galaxy by using some basic units about the speed of our solar system around the center of the galaxy, which is about 230 kilometers per second. And the average distance of the solar system to the center of the galaxy, which is about 25,000 light years. You have to do some conversions. SI units might work, but there's probably better units out there. But even that is an estimate of the mass of the solar system, or the mass of the galaxy, which is neat. As far as I know, you can't really do that for the speed of galaxies around each other because they're not really orbiting a common center. They just kind of have this motion due to their kind of superclusterness. So that's a little bit beyond what this model can do. But in keeping with this spirit, let's solve this equation, or let's substitute the velocity of the orbit for the period. So that's going to be 2 pi r over t. And so we can solve this for t. If we solve this for t, we have to square both sides and then cross multiply. And so if we square both sides and cross multiply, then maybe going up here, we get big G, mass of the central object divided by r, equals 4 pi squared r squared over t squared. And you can solve this for t, again, cross multiplying. The r's don't cancel in this case. In fact, the r's multiply together, and we're left with t squared equals 4 pi squared over gm times r cubed. And so there's a great example in the book about a graph that you see when you look at this equation. Now, this is an example of an equation that is a power law. By power law, we mean that both the variables are related to each other by some sort of rule. And I'm going to switch screens real quick to show you this graph. So you see here, I can go full screen real quick. What we can look at this graph now with a little bit more detail. This is a graph that's kind of at the beginning of the chapter and then repeated near the end. So all these planets line up. Why did they line up? Well, because these axes are not absolute. I mean, they're absolute, but they're not nominal values of period and radius. They are the logarithm of the period and the radius. And so the interesting thing to observe about this equation or about this line is that in this kind of region here, we got log of t equals 1.5 log of r minus a constant. Where does that quantity come from? It is derived from Kepler's law. I can show you real quick. If we start off with the equation that we had just derived, t squared equals 4 pi squared over gm times r cubed. If we take the log of both sides, if we take the log of both sides, then we're going to get on the left-hand side, we're going to get 2 log of t. And that's going to equal, there's a lot of work you can do here, but it basically means that it's log of everything, or natural, or log of everything in that parentheses plus 3 log of r. Remember, when you take the logarithm of the quantity raised to a power, that power just gets pulled out by the property of logs, where the log of a product is the sum of the logs. And so evidently that constant, which has got a bunch of things in it, that log of this parentheses technically equals log of 4 plus 2 log of pi minus log of g minus log of m. And evidently all of those add up to this constant this constant that you see here, this negative 9.264. But we see here that the graph, the slope of this line, is, if we divide the 2 by both sides, oh, I guess you got to divide by 2 as well. But the slope of this line is 3/2. So rise in 3, and you go over 2. The units of this slope, got to be a little bit careful about what the units are. But that's the idea of a log-log graph, because typically in problems in science and engineering, you might be dealing with quantities that range over a wide range of values. One that I can think of is the electrical properties of different materials. Some are extremely electrical, some are not electrical at all, and those properties range over many orders of magnitude of 10. And so it's helpful to graph things like this in a log-log plot to straighten out the curve. And the slope of that log-log plot is actually how these quantities are related. So that's a good technique to carry forward with you in future classes. Of course, the planets are actually moving in an elliptical orbit, and so Kepler's law for an elliptical orbit reduces to an average of the distance of the object to the sun. So I'm going to switch back to the whiteboard now and talk about energy. So we don't need to erase too much of this, but we just need to know, well, I'll just start over. Because this chapter, while the content in it is really interesting, the techniques that they talk about really extend in a wide range to other areas. So let me draw this picture again and remind you that, so if the velocity of orbit, or if the speed of orbit of an object is square root big G little, or big G big M over little r, again, r is the distance, big M is the mass of the central body. What's the energy? What's the kinetic energy of the object, first of all? Well, clearly, the kinetic energy is 1/2 mv squared. And this, when you square the speed right here, the gm over, when you square this speed, this gm over r, you find that the kinetic energy equals 1/2 m times big G, big M over little r. But observe that I'm not doing anything special here, just switching the things, switching the values. Notice that it looks like gravitational potential energy. We defined in a previous conversation that the gravitational potential energy of an object near the motionless planet is minus gmm over r. So it turns out that the kinetic energy of this system is actually minus potential energy over 2. Now you might be wondering why we're calling the kinetic energy negative, because it certainly needs to be positive. And of course, we're defining the potential energy for attracted objects that are always feel an attractive force is always negative, right? Because as they get closer and closer together, that attractive force does positive work and therefore makes an already negative kinetic or potential energy even more negative. So what's the total energy then? If that's the kinetic energy, the total energy, the mechanical energy, if you want to call it that, which is obviously kinetic plus potential. Now we can plug this in. So it's minus, I'll just go below, minus u over 2 plus u. So you're really just doing minus 1/2 plus 1. And so the total energy is not minus u over 2, but plus u over 2. But once again, the u is negative, so the total energy of this system is negative. And this is another, so I've arrived kind of at another interesting result that can extend to other areas of science. And that's the concept of a negative total energy. A negative total energy is indicative of what we call a bound state. So systems like this that feel forces, that conservative systems, they feel attractive forces and the objects might be moving. Evidently, the attractive forces and the energies associated with them are bigger than the kinetic energy associated with their motion. In fact, we see here that the potential energy of a planet or of a satellite is actually in numerical modulus about twice as big. And so the system is what we call stable. The object is bound towards the gravitational pull of the object. And you can extend this into further scales to argue that the solar system is stable. If you think of the solar system, right, there's the sun at the middle and all of the, right over here, the sun in the middle, and then all the orbiting planets, right, all the junk, right, the asteroid belt, and then further out you got the gas giants. What's the total energy of the solar system in the coordinate system of the sun, where the sun is at the center? Well, once again, you need to know the speed of all the planets and therefore their kinetic energies. And if you add up the kinetic energies of all of the planets, everything orbiting the sun, it's still in numerical value less than the total potential energy shared between every object. Because what's the potential energy of the solar system? Well, you technically need to calculate the shared potential energy between every pair of objects in the solar system. And you can't count it twice. And so, for instance, if you have just considering the sun and all the planets, if there's nine objects, the 8 planets and the ninth object being the sun, then there is 9 choose 2, which 9 times 8 times 7 factorial over 2 times 7 factorial, there is 36. 9 times 8, 72 divided by 2. There's 36 different potential energies that you need to calculate. And you need to calculate potential energy between Jupiter and Mercury, potential energy between Earth and Venus, between Venus and, you have to choose 2 for each potential energy and add all those up. And that certainly will change, as the planets orbit. Their distances between each other shifts, and so the potential energy shifts, but evidently that total number of all of those potential energies, then it's negative, and it's even added with the kinetic energies of all of the objects moving, it's still a total energy is still negative. And so the solar system is another example of the fact that it's a bound system. You could even go further out and think about a galaxy. The total kinetic energy of all the orbiting stars versus the bound potential energy between them and between the center of mass of the galaxy is still much more negative than the kinetic energy is positive. But this extends all the way into the other scale as well, at the molecular, atomic, and nuclear scale. Right? You think about a basic molecule, say like a water molecule, just to have a picture, right? We got 2 hydrogens and an oxygen. How are these two, how is this molecule formed? I mean, there is some sort of intermolecular attractive forces between these particles, and therefore there's a potential energy, right? There's potential energy associated with these two, potential energy associated with these two, perhaps this is certainly like an attractive potential energy, like a plus and a minus. Also, same here, plus and a minus. Well, there's a slightly repulsive potential energy between the 2 hydrogen atoms, but still those add to a total potential energy, which is negative. But these also have an inherent motion in some sort of center of mass coordinate system of the molecule. And they have a motion, a vibration, maybe a slight rotation. All that kinetic energy is still less than the negative potential energy. So the total energy of a water molecule itself is also negative. And you can go further into matter, like the atom also has a negative total energy. Except if it's radioactive. If it's radioactive, then maybe it has a positive total energy, because if a system has a positive total energy, that means the kinetic outweighs the potential. And so it's got enough energy to, say, escape the pull of the other objects. And we call that a scattering state. But even in the atom, a stable atom, the total energy of the atom is negative. And even inside the nucleus, protons and neutrons that comprise the nucleus, they feel such strong attractive forces that their vibrational energies, the energy associated with the motion of their vibration is not enough to overcome the strong potential energies from their fact that they're attracted to one another in the nucleus. So once again, another example of total energy and how gravity is a good template for other examples in physics and science. The last thing I want to mention then is a model of how you go using energy, how you go from one orbit to the next. So say we're at a pretty low orbit, right, for the object in the middle, and we want to go to a bigger orbit. The book offers one suggestion of how to do that. The first thing to note is that these speeds are fixed. Let's say if you need to go like twice as far out, then the speed will be smaller. So this is, let's label everything related to the inner orbit 1. So this would be R1, V1, and then everything associated with orbit 2, R2 and V2. So the total energy, if you look at an energy diagram of these objects in circular orbit, something that the book focuses on is drawing these energy diagrams. The total energy of a particle at the center of this system kind of goes like this, decreases down to infinity. It doesn't actually go to negative infinity, because eventually you'll hit there's some point where you hit the radius of the planet itself, and the potential energy changes after that. But if we're farther out, R1, R2, then this is a graph of total energy for an orbiting object. And so what that means is that the total energy must increase to go from lower orbit to higher orbit. So there needs to be this, maybe call it delta E. Where are we going to get that energy to go from one orbit to the next? Well, work. You have to do work, and say if this is like a rocket that's orbiting the middle of the central orbit, you have to fire your rocket to increase, it's going to do work to increase the kinetic energy, and it'll increase the kinetic energy enough to where basically if you do work to increase the speed, then the orbit will become elliptical. And if you increase it just enough, the orbit will be elliptical, and it'll barely just have the speed it needs to go to that outer edge where these are lined up. I know this isn't perfect, but then you have to do work again. You have to do work to make this elliptical orbit turn into a circle. And so this is one suggestion of how to go from one orbit to the next. You just fire your thrusters in 2 stages. One stage is right here to turn the small circular orbit into an elliptical orbit, with its farthest point at the edge of the bigger circular orbit that you're trying to get to. And then fire your thrusters again to get to the actual circular orbit. And so it's interesting to consider how that energy is added to that system. And of course, that energy comes from, for a chemical rocket, it just comes from the combustion of fuel. And the problems that we did for momentum would be helpful to understand how that energy increases. Because of course, in a rocket, if you burn fuel, then you lower the mass of the rocket. So that actually works out to your advantage because the force is accelerating and increasing the energy at a rate that's better than if the mass was constant. The end of chapter 13 has an example problem similar to this, and there's even one near the end of the chapter, problems, that is interesting to calculate these too. So that is an overview of chapter 13. There's certainly a lot more topics to cover in chapter 13. Several topics that Newton's theory of gravity does not, for instance, cover. And one, so, it's a fantastic theory to launch satellites into low Earth orbit, even into the lunar orbit. Certainly appropriate of a theory to get us to Mars. When you get to the sun, Newton's theory of gravity, it doesn't break down, but it becomes ever so slightly less accurate of a theory. And that's because the sun is so massive that it starts to bend the space around it. So light doesn't travel in straight lines anymore around the sun. It travels in ever so slightly bent curves. And so that is not described by Newton's theory of gravity. Some other topics about Newton's theory of gravity that are cosmology that aren't mentioned would be dark matter and dark energy, and then black holes, and of course the expansion of the universe as a whole. So those are interesting topics that this book or this chapter doesn't talk about, but this is the end of chapter 13.